Welcome to 3.11. This is the last lesson of Unit 3. We're going to apply the appropriate derivative rules to evaluate the derivative for advanced functions and in order to solve AP level questions. Let's go ahead and get started. So whenever we're solving a problem and we come to a point where we decide we're going to need to take the derivative of a function, we don't want to spend hours and hours actually taking that derivative. And we'd like to make sure that we find the most efficient route, because oftentimes we can waste a lot of time doing something that can be done pretty simply. So what you want to do is create an efficient protocol, meaning a step-by-step process for finding the derivative of any function. It needs to be general, meaning that you need to be able to just apply this to any situation. So it shouldn't be really specific, like, oh, I'm going to apply the power rule to start off with. Well, you might not want to apply the power rule to start off with. So it just needs to be something that your head is able to quickly go through when finding the derivative, so that you will lead yourself to the most efficient method. And to test your protocol, your step-by-step process, you might go and test it out on a couple problems that you've already found the solution to make sure that it works. So go ahead and do this for yourself. This should certainly go in your notes, and also would be a good thing to add into your definitions and terms packet. So go ahead and do that. I will talk a little bit about how I go through taking a derivative, and so you could potentially pull some things from my protocol. Okay, here's my sort of step-by-step process that I go through. And I want to make something clear. There are some derivatives which are really easy to take that I don't need to go through this whole step-by-step process. You know, if I just am taking the derivative of 4x squared, I know it's going to be 8x, right? I've memorized my power rule. So you shouldn't be relying on going through this whole step-by-step thing as if it's some laborious task. This is just the way that you think about taking the derivative. And so if it's a simple derivative, 4x squared, it's not that I'm not going through this protocol, it's that it's very easy for me to go through all of these steps in a split second. So here's the overarching picture that you need to have in your mind. The derivative of a function f of x is the slope. So if ever you are feeling overwhelmed or confused, remind yourself of that. It's nothing crazy. You know the definition. It's just a limit, and it's just finding the slope at any point. And so if you need to, look at the graph, right? If this is a function that you just have absolutely no idea about, you have no clue, there are no rules which you'll be able to come up with, you can always go back and look at the graph and at least get some idea of what's going on. Okay, so keep that in mind. That's the overarching idea. First thing I look at, which variable am I differentiating with respect to? WRT with respect to which variable? It's in almost all cases going to be x. However, there are a couple of times we've seen where the variable that I'm differentiating with respect to is theta. So in almost all cases we're going to see x, we've seen t, and sometimes we'll see theta. We'll see a bunch of others by the time we're done, but make sure you know which variable you're actually differentiating with respect to. And this is of course very important, because any variable that you're not differentiating with respect to, that doesn't matter. That's a constant value. It's not the one that you're thinking about the change with respect to. Next thing that I do is I look to, I identify where those variables are, right? I make sure I know where they are in the function itself. And then I simplify. I factor out any constants, some common constants that are in there, pi, or just any number. Then I try to write the radicals in exponential form. Right? If I see a square root, I can write it as 1/2. That can be helpful. And then using the sum and difference rules are also helpful. If I have a big sum or difference of things, I know I can take the derivative of each one independently. That can make my life a lot easier. So I could break it up into some smaller problems and tackle them one at a time. The next thing I do once I've got that squared away is identify the overarching function / rule. And this is important, right? If overall you just have a quotient of two functions, you know you're going to apply the quotient rule, and that anything else that you do will be within the quotient rule, right? If you see that you have a situation like, sine of e to the x, you know that you're applying the chain rule because you're taking the sign of another function. And so that's going to be the rule you're going to use first and foremost. Then what I try and do after I identify that overarching rule is in my head I try and go through what would then have to happen. So I try and project forward. If I'm doing the quotient rule and I have kind of a complicated numerator and denominator, I try and look at each one and see, since I know I'm going to take the derivative of each of those, that u and v, I kind of look ahead and say, will I need to use another rule? Will I need to use another quotient rule, another chain rule? Whatever it is. Is it a trig function, an inverse trig function? And just so that way I can kind of see the end of the tunnel before I dive in and get, all wound up and lost. That I think is a really key point and will help you remain organized, which we'll talk about. Then I write down the rule, that's the overarching function rule that I have decided on, and I make a u/v substitution if I need to. So if this all depends on how you feel best organized. I think this can be really helpful. Sometimes you can just label what u and v are going to be, but if you actually say u is this, v is this, and then you write down your rule with u and v, you can literally just plug them back into your rule, and that can really help you stay organized. But it's important to write down the rule as a reference so that you don't forget. And just by doing that, you're going to actually increase your ability to memorize any rule at any time and recall it. Once I've done that, then I begin to solve. And the key here is to remain organized. So if I'm using the quotient rule, I try to keep the quotient rule and that whole process as my main piece. If within the quotient rule I'm taking the derivative of, let's just say, a trig function that is, it has a complicated function inside of it, I take that and go off to the side and do that off to the side and then come back to my main process with my quotient rule and put back in what I found for the derivative of that function. That's really important and will help you stay organized. And that's the key. You've got to stay organized, and when all else fails, keep in mind that you're simply evaluating the slope of the function at any point. And so no matter what, you can always go back to the graph of the function, the original function, look at it, analyze the slope, and that will give you an idea of what your derivative should eventually look like. This isn't by any means what your protocol has to be. If you think of it a little differently and it works perfectly for you, that's fine, but this is how I think it through, and you're welcome to steal any part of this / all of it and use it for your own successful derivative evaluation. We're going to take a look at one kind of complicated question together, and then I'm going to give you some more to try on your own and test your rule, your protocol out on. All right, so here's my function. It's the square root of 3x minus 1 over sine of x squared. And I can easily see that I'm differentiating with respect to x, and there's really nothing that I can factor out. However, I can change the way that I represent the radical so that I can represent it as a power, which will allow me to utilize my power rule. So that's actually the first thing that I'm going to do. I'm going to rewrite my function as 3x minus 1 over sine of x squared all to the 1/2. So now I can see pretty clearly that I'm going to be using the chain rule, and I'm going to be applying that to this outside function, which is raising something to the 1/2, and then I'm going to have to take the derivative of the inside. So I'm actually going to write down my rule, and the rule is that if I take the derivative with respect to x of some function u to the n, then the derivative of that will be n times u to the n minus 1 times the derivative of u with respect to x. So what I can do here is actually name my u, and this is kind of up to you how you best see it. I can clearly recognize that this is my function u and this is my value n. And so I can actually take the derivative and do that without making a clear substitution. But if you struggle with that and you find that you're making errors, I highly encourage you to actually write out your u substitution. So what you say is, let u be equal to 3x minus 1 over sine of x squared, right? Your inside function there. And now you can rewrite your function f of x as u to the 1/2. And that makes applying your rule really easy, because you just go through and you say, okay, now n is 1/2, so it's going to be 1/2 u to the negative 1/2 times the derivative of u. So let's go ahead and write that out. F prime of x is going to be 1/2, and here I'm just going to put in for u 3x minus 1 over sine of x squared, all raised to the negative 1/2 power, times the derivative with respect to x of the inside function, or of u, and u is just this piece here. So the derivative of 3x minus 1 over the sine of x squared. And this is what I was preparing for all along. I knew I needed to take the derivative of the inside, which was going to require the quotient rule. And in fact, sine of x squared is going to require the chain rule again. But this will be pretty simple. So at this point, I want to keep the flow of my quotient rule. I want that to happen outside here, because I'm applying the chain rule. I know when I finish all of this, I'll have the derivative of f, and so I don't want to do too much in here that could lose some pieces. So I'm going to go off to the side and actually compute this derivative. All right, so here I'm going to go off to the side. I know I'm going to apply the quotient rule, and I'm going to let this be u and this be v. And so I'm actually going to write out my quotient rule over to the side. So if I have u over v, and I'm taking the derivative with respect to x of that, then what I'm going to have is v times u prime minus u times v prime all over v squared. So I can go ahead and apply that. I can write this out in terms of u and v if I want to, but I think that's a little bit of a waste of time, because I can clearly see what each is. So I need v, which is sine of x squared, times u prime. Now I can take the derivative of this in my head pretty easily. Derivative will be 3 minus u, which is 3x minus 1, times the derivative of sine of x squared. Now, you know sine of u is cosine of, the derivative of sine of u is cosine of u times the derivative of u. Well, the derivative of x squared is 2x. So the derivative of the inside will be 2x times cosine of x squared. And that's all going to be divided by sine of x squared squared. Sine squared of x squared. Now at this point I can look to simplify, but there's really not a whole lot I can do because this is sine squared. You know, I could cancel out a sine of x squared here and split these two things up, but I'm going to go ahead and keep it like this just because that's not going to be that advantageous. And when I come over here, since this is raised to the 1/2, what I can do is I can invert this. I can go 1 over this to the positive 1/2. And so then when I do that, I'll see if I can combine anything. And if not, then I'll just be done with my derivative. It'll be a little complicated, but at least I know I've got it done correctly. So right now I'm going to go ahead and move this piece back in. So I've moved this piece back in, and I've changed the negative exponent to a positive. And notice that all I've done is flip the numerator and denominator. Remember, if I have 3x minus 1 to the negative 1/2 and sine of x squared to the negative 1/2, to make each of those positive, I switch the role in the numerator and denominator. So this would move to the numerator and be sine of x squared to the positive 1/2, and this would move to the denominator and be 3x minus 1 to the negative to the positive 1/2. So then I can pull the positive 1/2 back outside. Basically, I'm just flipping the numerator and denominator and making the exponent positive. At this point, there's really not a whole lot I can do besides rewriting this as a square root if I wanted to. So feel free to go ahead and do that. But other than that, I'm just going to keep it in this form, and unless it's a multiple choice question and it asks for it in a slightly different form, then I could try and make some manipulations. But other than that, I'm just going to keep it in this form. All right, I'm going to give you some more to complete on your own. These will require a little more work, so be ready to put that work in. It will be very worth it, however, so make sure you spend your time wisely. Here we go. All right, here they are. Go through each one. Take your time with some of them may go quickly, and make sure that you're ready to present them on Monday.